Lesson 7, derivatives. Okay, in this lesson, what we're going to be doing is defining what a derivative is. We're going to find a general derivative of a function using first principles, which I'll show in a second. We're going to identify points where a function is non-differentiable, and we're going to graph the derivative of a function, so just a general sketch of the derivative function. Okay, so what is a derivative? Well, I've kind of been leading up to this. You've probably guessed what it is from my other lessons. But let's say that you were in Physics 20, which a lot of you guys have taken, or maybe even Math 10C or something. Well, remember this example where we had like distance and we had time, right? And maybe our function looked like if you graphed it all out, it looked something like this. And then what I had you doing was figuring out the instantaneous velocity at any given point. And the way we did that was we drew a tangent line. That should be familiar, the word tangent. But we drew a tangent line, right? And then what we did is we just figured out the rise and run of that tangent line, and we were just kind of estimating it, right? We just did the best that we could to make that line tangent, and then we'd figure out the the rise and the run, and we just did it that way. And that figured out the speed, right? Because on a distance time graph, the speed is the slope of the graph, right? Okay, well, that really is the derivative, right? The slope of the graph at any given point there would be the derivative of that function. And that's pretty much it. So you guys just need to get in the mindset as we're going through here that the derivative is the slope of the function, right? The slope of the tangent line, right, that we just drew there at any point on that function. Okay? So that's going to be what we're talking about with the derivative there, right? And it is, so it's the slope of the tangent line, which would also be a rate of change, right? Meters per second in this case, right, with my graph. But we'll get more into that. We have a whole unit on applications. So, okay, so if we need to figure out the slope of the tangent line, well, that seems like we gotta look back to our equations from before, right? This really is just taking the limit of the slope, right, of the secant line, so to give you that tangent line at that point. So this is exactly what we did last lesson. Really, now we're just going to be calling this the derivative now. We're just being more specific about it. Okay, a couple of new notations, though, that we're going to be using is, like, do you see that little tick on the top there? That's called prime, that symbol. So whenever, so the way this would look is, that you'd say this would be the derivative of a, right? And we just know that because of the prime symbol there, or sorry, derivative of f of a. Okay. Yeah, so we'll go down and do a few more of those. Now, I just want to show you there are actually different ways of different notations for showing the derivative. The first one would just be y prime, right? So yeah, instead of f, we use y, which we do quite often in math anyway, right? You guys are probably used to changing it between y is equal to 2x plus 3 and f of x is equal to 2x plus 3, right? Same thing. So we'll just y prime or f prime or f of x prime, right? Those are all really the same thing. And then this one will be kind of new, and this is the Leibniz notation. So if you remember from the beginning class, we talked about how Newton and Leibniz were kind of like created calculus at the same time, just almost by chance, right? This was more of his notation. And to tell you the truth, this is really a common notation, especially when we start doing what's called implicit differentiation and stuff a little bit later. Okay, but for now, yeah, and I'll get more into this as I use it. I'll explain kind of what this is showing. But the way you'd say this, it would be the derivative of y with respect to x. And the d's, you can almost think of those kind of like change in y over change in x. It's kind of the same idea. Quite often d's are meant to kind of show like change in. So, and not really. This really means like the derivative, right? It's explicit, but you can kind of think of it in that way. Okay. So this question says, if f of x is equal to 4 times 2x minus 7 to the power of negative 1, find f prime of x, or the derivative of x, and f prime of 2. Okay, so the derivative at 2, right? So remember what we're looking for here. We're looking for the slope on that function, right? This one would be like, find the general equation that I could just plug x in and get the slope any time. And f prime of 2 would be saying what is the slope when x is 2, right? The slope of the tangent line when x is 2. Okay, so a good strategy here is actually to figure out this one first, and then we can just plug x in to figure out this one, right? All right, so let's do that. So let's rewrite this thing first, though. I'm not a big fan of the way this looks, so I am going to write it like f of x is equal to, and then leave the 4 in the numerator. And then since this is -1, I'm just going to put that in the bottom. So this would be 2x minus 7. Okay? So now, well, remember what we have to do. The derivative of this would be the limit as h approaches 0. And then we're using our equation from before, right? This is first principles. So 4 over 2, and then instead of an x, right, I'm going to put in x plus h minus 7. Okay, and then minus, and then 4 over 2x minus 7. So if you're having trouble with that, just remember what that was. That was just from this equation, right? Right? That was f of x plus h minus f of x. So this was just throwing in x plus h in for x, right into that. And then this really was just f of x, right? That was our function, okay? All right, so that's where we're starting. And then over, all over h. So you can see right now the way we'll end up with a 0 over 0 situation. So we need to simplify this. So probably the best way to do this is to get a common denominator going. And I think the other thing I'm going to want to do, I'm not a big fan of the way the denominator of this part's looking. So I'm going to expand that all out. See if I can make that a little simpler, maybe. Okay. So I'm going to stop writing the limit for a second, just because I'm lazy. Okay, so this would be 4 over, and then expanding this all out, we would get 2x plus 2h minus 7, okay, minus 4 over 2x minus 7. And that was all over h. All right, so now we're pretty good to go. I think that's kind of everything we can do here. So now we're going to combine that top one over the same denominator, right? So this would become 4, and then multiplying it by this bottom, right? Because I have to multiply both sides. So 4 times 2x minus 7, and then minus, and then the next part, 4 times 2x plus 2h minus 7, all over, and then all over our common denominator, right? So 2x minus 7, and then 2x plus 2h minus 7. Okay, and then that was all over h, right? That was all over h. But you know what? Just to avoid confusion, you can see right now, like this would be like h over 1, right? And if I multiply by the reciprocal, can you guys see that the h would just end up in the bottom here? So I can get rid of that. That would just make my life a little bit easier, right? So that's just in the denominator now. If you want to write it out the other way and then multiply by the reciprocal, you'd see that you get the same thing. But I'm just going to skip to that, right? Just to kind of give myself more room and make it less confusing. Okay, so that's where we're at so far. So now what we're going to do, we're just going to expand everything out on the top. So we've got 8x minus 28 minus 8x minus 8h plus 28 all over h times 2x minus 7 times 2x plus 2h minus 7. Okay, this is going to work out nice too, isn't it? Because I've got positive 8x, negative 8x, I've got negative 28, positive 28. I'll give you a little hint here too. When that happens, right, when I get to that point, you know you did it right too, which is actually a good thing, right? Like if those don't cancel out and you can't cancel your h, something's going wrong, right? You're doing something a little off. So just go back and check. But either way, so now we can see if I cancel those out, I'm not going to write it all again just because I'm getting lazy again. I'm going to go ahead and cancel my h, right? Because all I would have up there is that top term. So I'm just going to cancel h with h, right? And there you go. Now we should be good to take the limit of this, right? So I'm going to write it out one more time. So we'd say the limit as h approaches 0 of, and then all I have left is negative 8 over, and then the bottom here, right? 2x minus 7, and then 2x plus 2h minus 7. Okay, so remember what we do. So we just put in h is equal to 0, right? We'll actually put in 0, so this will become 0, right? So there's our derivative. We can say f prime of x is equal to 8 over 2x minus 7 times 2x minus 7. So then I should clean that up a little, right? We'll just call that negative 8 over 2x minus 7 squared. And there you go. That is our first derivative. And now just remember what we've done. We've just made an equation for finding the derivative, or finding the slope of the tangent line at any given point, right? Which is a powerful tool. This comes up a lot. This is what mathematicians, this is what physicists do all the time, right? When they're coming up with an equation, like the fancy equations on Big Bang Theory on the board, they're quite often taking the derivative of something to find a new equation for whatever, right? Okay, so let's write that down for your notes too. This would be the general slope equation. All right. Now, next part says the specific point, right? So that was part 1. Now part 2, it said, let's see, specific point. F prime of 2 is what we were after. Okay, well now that's easy. Now we can just plug in 2 in for x, right? So this would just become negative 8 over 2 times negative, or 2 times 2. They say negative 2? Sorry. 2 times 2 minus 7 squared. So f prime of 2 is equal to negative 8 over 9. All right, let's do another. Find dy dx for y is equal to the square root of 5 minus x. Okay, so again, dy means the derivative of y with respect to x. Okay, I'll get more into that again later, but for now, we'll just picture it as the derivative, okay? So dy dx is equal to the limit as h approaches 0 of, okay, so then it'll be the square root of 5 minus, and then instead of an x, I'm putting in x plus h. Okay, and then minus the square root of 5 minus x, right? That is f of x, all over h. Okay, so now in this one, I think what I want to do here, well, I think we're okay with, instead of writing another line with simplifying this up, I think we're okay just to kind of do that part in our head, right? That'd be 5 minus x and minus h, right? So I'm just going to multiply the top and bottom by the conjugate pair, right? I'm going to rationalize the numerator here. So this would become, maybe a different color, square root of, and then I'm going to write what that simplified would be, okay? So that'd be 5 minus x minus h plus, right, the conjugate pair, 5 minus x. And then same on the bottom. 5 minus x minus h plus the square root of 5 minus x. Okay. And then since these are conjugate pairs, right, I only really have to think about multiplying the first two terms and the last two terms because I know the middle terms are going to cancel, right, which is nice. So let's write this out again. So we've got, this is equal to the limit as h approaches 0 of, so it works out nice with the square roots too, right, because that first part just becomes 5 minus x minus h, right, for that first one. And then the second one would just be minus 5 minus x. Over our new bottom here, right? So now we have h times the square root of 5 minus x minus h plus the square root of 5 minus x. Okay, and then, yeah, if we simplify things out here, the 5 would cancel with, well, this would be negative 5 once I distributed the negative in, right? So this would be, 5's cancel out. And then same with the x's, right? Negative x, and then when I distribute this negative in, that'd be positive x, right? So the x would cancel too. So all we're going to be left with here on the top, oh, sorry, x cancels too, is going to be negative h, right? So then we have, all right, one more time, the limit as h approaches 0 of negative h over h, and then 5 minus x minus h plus, oh, that was the square root, plus the square root of 5 minus x. Okay, and you can probably see here now with the h's that they would cancel, right? And if we keep going here, we'll throw in, I'll throw in 0 right now, right? So throw 0 in for h. So our derivative would become negative 1 over, and then it would simplify it. There would be just two of them, right? Because the h is gone. I've got two 5 minus x's. So I'm going to call that 2 root 5 minus x. And there you go. There's our derivative of that function. All right. Okay, so where can we and can't we take the derivative of a function? Well, in general here it says the function f is differentiable at a if f prime of a exists. Okay, that's actually kind of almost like a common sense one, right? So that's kind of saying we're able to differentiate it, we're able to take the derivative if the derivative exists at that point, right? So just give you a quick example, kind of cut to the chase here. If we had a function that was like doing, all kinds of curves and stuff, which we can take the derivative, but then all of a sudden came up to a point and then back down again, right? Like just a sharp corner, then that becomes a little bit tougher to figure out what the slope at that sharp corner is, doesn't it? Right? Like, is the slope like, there, or is it there, or is it flat, right? It could actually be any of them if it's like at the peak, right? So you can kind of see that that wouldn't be differentiable, right? I can't take the derivative at that point, okay? I also wouldn't be able to take the derivative, let's say if I had a function, oh, I'll do blue. If I had a function, doing whatever, and then just stopped, right? Because if I looked at that point there, again, you can kind of see that, okay, what would the derivative be at that point? Well, if I'm at a point, maybe it's like, the last part, like where it was, where the slope was before that point. But it wouldn't quite be that either, because if you go right on that point, it's like it could be there, for the slope, it could be like there. Like, we don't really know when it comes to a direct, like to a stop like that, right? Because there's nothing that, like, we can't take the limit from both sides. You can think of it that way too, right? If we're finding the limit of the slopes, so it doesn't work out. So, okay, so that's kind of the idea, which I think almost it just makes sense to me. But okay, so show that the function. Oh, sorry, I was getting ahead of myself. Where is the function in example 2 differentiable? Okay, so the function in example 2 was f of x is equal to 4 over 2x minus 7 from the last one. So where is it not differentiable? Well, you can look at the restrictions on the original too, right? Like if you actually graph that out, we could figure out where the asymptote is, right, on this. We know because you're dividing by 0 there. Yeah, so if we actually just solve for that, right, like we could solve for that even now, right, where you could say it's going to be at 7/2, right, is where it's not going to be differentiable because there'll be an asymptote at that point, right? Like it's never going to approach it. How do I figure out the slope of that point, right, whatever that is? So we can't find the derivative right there, so I know that right off the bat. But sticking to our definition here, well, I could also look at the derivative of f of x, right? And that ended up being -8 over the square root of, 2x minus 7 squared. And we end up with the same thing, right? This is still going to be where we're dividing by 0. So let's make ourselves a little equation. We'll say, okay, 2x minus 7 cannot equal 0. So then solving for this, you'd say x cannot equal 7/2. Right? So it makes sense. So we should probably do this right and say, therefore, f of x is not differentiable at x is equal to 7/2. All right. Show that the function f of x is equal to the absolute value of x is not differentiable at 0. All right, so let's write it out. So we'll say, okay, the limit as h approaches 0 of x plus h, the absolute value of x plus h, minus the absolute value of x over h. Okay, so that's what we're after, right? So now, what if the slope, here, let's do it this way. So, what is the slope when x is greater than 0? Okay? Well, let's kind of sketch this out for a second. So right now, the graph of the absolute value of x, we know, would look like a V, right? Goes up there, and then it goes up there the other way, okay? So if x is greater than 0, right, so it just means everything to the right here, then this would be following the function f of x is equal to x, right? That would be the function x, or it's like just y is equal to x, right? Goes up 1 over 1, up 1 over 1, right? So that's generally the graph that we'd be looking at. So if we did that, right, if we actually just use x as our function instead of the absolute value of x, then what we can do is we'll say, okay, then f of x, or sorry, f prime of x, the derivative, is equal to, and then we'll use x instead of the absolute value of x for now, okay? We're just looking at the right side of this thing. So we'll say the limit as h approaches 0 of, and then this would become x plus h and then minus x over h. And this works out nicely because I've got x and they cancel. So then this would be the limit as h approaches 0 of h over h. So that'd be equal to 1, right? Because the h is a cancel, and then I can't really put 0 in for anything. There's no h to put it into, right? So it's 1, which makes sense, right? The limit would be 1. The slope would be 1, right? 1 over 1 at any given point. So that makes sense, right? For that side of the graph. But now let's flip to the other side. So what is the slope when x is less than 0? Okay, well, when it's less than 0, you can see it's kind of it's following this line, right? And that line, up until this point, and that line would be, that was terrible. We'll say f of x is equal to negative x, right? That would be our new equation. So let's do that one. So that would be f of x, or f prime of x, is equal to the limit as h approaches 0. And then this would be Now, negative x plus h, right? Putting the x plus h in for x. And then minus negative x all over h, which is equal to the limit as h approaches 0 of, again, all my x's cancel if you expand all that out, but I end up with negative h over h, which would be negative 1. And again, that makes sense, right? This would be going down 1 over 1, right? So that would be my slope on that graph, right? Okay, so that's probably enough logic that we could kind of say that the limit doesn't exist here, right? Because you can kind of see it. The limit on the right is 1, the limit on the left is negative 1. We can see that they're not going to correspond. But let's write this out the right way. So we'd say it like this. We'd say f prime of 0, right? F prime at 0, or the derivative at 0, is equal to the limit as h approaches 0. So then this would become the absolute value of 0 plus h minus the absolute value of 0 all over h. Okay, so the zeros obviously just cancel there, but we still have a problem. This would become the limit as h approaches 0 of the absolute value of h over h. Okay, now the problem is here, so we could think of this in two different ways now. We'd have to go from the left and from the right. So we'd say the limit as h approaches 0 from the left, right, the little minus sign there, of absolute value of h over h would be equal to negative 1, and the limit as h approaches 0 of the absolute value of h over h as h approaches 0 from the right is going to be equal to 1. So then we'll just say the limit as h approaches 0 from the right, well, from the left, I guess I did that first, from the left, does not equal the limit as h approaches 0 from the right. Okay, so then therefore f prime of x does not exist. Okay. So in general, like I was saying above, actually, it's not differentiable at any sharp corner, right? For the reason I showed above, at any endpoint, or anywhere that the tangent line is vertical, right? And let's think about why that makes sense too, right? If you had a function that, like, let's say, went up and then like straight down again like this, I can't take the derivative of that because that'd be a line straight up and down. A straight up and down line is undefined, right? Because that's like I have a rise of infinity and a run of 0. I'm dividing by 0, right? So you can't take the derivative of a vertical line or anywhere that the function is just undefined. Okay. Now, graphical interpretation of a derivative. So just remember when you're figuring out the derivatives of these graphs, what you're really looking at, what you're really thinking about is what is the slope at that point. Okay. So let's look down at this example on the left first. So if you look at right here on this, like this graph of f of x here, well, right at the peaks are nice, right? Because the peak of this graph, I know that that's where we have a slope of 0, right? So if it was y prime, right, the derivative now, if I was graphing the new function, that point there where the slope is 0, well, remember, like our f of x or our y value, right? That's our derivative, so it should be 0, right? It should have a value of 0 at that point. Okay, so those are good starting points, right? Usually peaks anywhere that the derivative is 0. So it's going to be there, okay? And then again, you would find one here. The derivative of again is going to be 0. Now we're going to do a bunch more of this in the next unit actually with curve sketching. But you can also figure out like from that point. Let's say if I didn't know any of this, right? If I didn't have a drawing already made and all I had was my 2x intercepts, so I didn't know like which way it opened up or which way it started, like, you know, doing this. Well, I could figure that out from this too, right? Because if you think about, like, let's say the point right here, that would be a positive slope, right? So then, okay, positive slope. Positive slope on this graph means it would be above 0, right? So I knew beforehand, before this point, it was above 0. It was somewhere up here. I don't know what it is from the graph. And then here, right, that's a negative slope. So this thing's coming down. Okay, well, negative slope on my derivative graph would be below 0, right? That's 0. It's going to be down here, which makes sense. And then someplace in the middle, right, this thing is switching. Again, we'll do more of this later, but at this inflection point, it's called, it's switching from a negative slope. Well, it's switching from the slope, I guess, changing really fast, right, at the beginning here, right? Everything's changing really quick. And then in the middle, it's not changing very quick at all. And then it starts actually heading like the other direction, right, back towards 0 again, back towards 0 again. And again, we're going to have better ways of doing that here, like in the next unit. But for now, you could do like just a rough sketch, right? You wouldn't really need to know how far down this comes or anything. We're gonna do that later, okay? But then yeah, that's the idea. So actually, you know what? In general, we should probably write down what some of these rules are. So let's write this. We'll say in general. If we had the graph of f of x and then the graph of f prime of x, or the derivative of x, then any max slash min points, or it is where the slope, or m, is equal to 0, well, that's going to be our x-intercepts on this one, on the derivative. So that's going to be our x-intercepts, okay? So that was just this. Slope is 0, x-intercept. If we have a positive slope on the original, okay, well then that's going to be positive y values. And then the opposite, if we had a negative slope, then that's going to be negative y values. That was just this part, right? If this thing is a negative slope, that just means it's going to be down here. Okay, any inflection points? So an inflection point was this, right? It's where it's changing from going like down to all of a sudden curving back up again. So that would be somewhere in the middle. We'll talk more, like I said, about this later, but this would be either a max or a minimum. So this would be a max or a min. And then lastly, I should say sharp corners or endpoints, etc. We'd say it does not exist on the new one. Okay. So now let's look at this graph. So we want to make a sketch of the derivative of this function. Okay, so let's actually make a little table again there too. So we'll say, okay, on f of x, and we've got f prime of x, and let's do this for different intervals, and we'll use interval notation too. So on the first interval, so we'll say the interval, you know, we'll say 1, right? This will be from like here up to here, okay, just this section. So this will relate to interval 1. So this would be the interval from negative infinity to negative 6, just right there. We would say that we have a positive m value. Okay, so it's going up, right? So in this case, this means we're going to have positive y values. Okay, so I know that I'm going to be up here, right, for the first part of it. Okay, let's keep going here, though. So now the second part, so 2 is going to be, so part 2 is going to be where x is equal to negative 6, right, just at that point, we'll say. So at that point, I'm at a max, So what's that mean for the derivative? That means that I'm going to have it's going to be 0, right? F of x would be 0 at that point. All right, and then part 3, so right here, this would be a point of inflection, we quite often say, right there, right? So we'll say 3 would be where x, and we'll assume it happens right at -4, so we'll say where x is equal to -4, and this would be a point of inflection. Okay, so at that point, well, we know it could be a max or a min, but we could also kind of think about it this way, where I know to begin with on f of x, right, beforehand I'm up here, and then I know I'm going to cross at 0 at -6, so it's going to cross here, right? So if I'm on my way down, right, and then I cross, and then I know that I have a max or a minimum, what would it be? Well, this would definitely be a minimum, wouldn't it? Right? It's not going to be a maximum. So I think I'm safe to say that this thing would be a minimum. Okay, and then 4. So for 4, we'll say right here, so this would be similar to 2, right? So at 4, this would be where x is equal to -2. Okay, so this would be a min on this one. So this would make this equal to 0 on the next. All right, and then for this section, we'll call this 5. So this would be, again, in interval notation, this isn't a point. This is from -2 to 3. We'll just say that we have a positive slope. Okay, so that means we're going to have positive y values. Oh, maybe I should do this too. Okay. And then for 6, so 6 we're going to make right here, right at that point. So then at this one, this is going to be so x is equal to 3. And at this point, this is a max point. But what's really happening there, right? It's a sharp corner. This is going to be, does not exist. And then 7. So 7 will be from here. This would be from 3 to infinity. We have negative m values. Okay, so these would be negative y values. All right, I think we have it all together, so we can put this thing together. So, okay, let's do our first section there. So we know that, well, I should tell you what, it's usually easiest to put our zeros in. So we know we have a 0 at -6. So 1, 2, 3. So it's right there. We know we have another 0 at -2. Okay, and then we knew that we were into positive y values, right, up here. Okay, so there's our first section. And then in between there, right, we knew we had a minimum. Okay, so I'm not exactly sure where that minimum is right now, but we know we have a minimum. Okay, so let's just do something like that, and then it would have to go back through again, wouldn't it? All right, so now the next part, we know that we have positive y values, which is looking good, right, because we're heading into the positive y value domain. And that's going to happen from -2 to 3, right? So it's going to keep going up to, you know, somewhere like that. Now again, I don't really know how high to come with this point, but I'm just kind of generally doing this. And then at this point here, well, it does not exist, so I'm going to make an open circle there. Okay, and then just lastly, the very last part, we have negative y values, and this is a straight line, right? I can be pretty sure that this slope or this derivative, right, would be the same everywhere. It's gonna be one line, right? So I'm expecting this will be a horizontal line somewhere. Okay, and actually I know enough. I know how to find this slope. This is down 2 over 1, right? So this would be down at -2. Okay, so down at -2. So again, this point doesn't exist to begin with, but then would go this way.